So in chapter 3, or in section 1.3, we talked about applications where we went through the stuff and then we set up differential equations, but we didn't solve for it because we didn't know how to solve for any of those differential equations yet. So now that we've got some practice solving for things, we will solve for these differential equations. And hopefully we'll remember what happened in 1.3 where we're actually just setting them up. And so the idea now is to set up, solve, and then be able to answer more questions if there are more questions. We'll start off with this linear model, or section 3.1 talks about first order linear differential equations. 3.2 will talk about first order nonlinear differential equations. And section 3.3 will talk about systems, and we'll not solve anything because we don't know how to solve systems, but at least we'll talk about modeling in that sense. So this first example we're going to look at is Newton's law of cooling, which we hopefully have seen before. And the general differential equation says that the rate of change of temperature is proportional to the difference between the current temperature and the temperature of the surroundings. So this is going to be our first example. And we'll use forensics as our application for this Newton's law of cooling. So here we have, they talk about a dead body found in a closed room. The house or temperature was constant at 70 degrees Fahrenheit. Ooh, what's this? Why is there quotes there? At the time of discovery, the core temperature was 80. So we don't know when it was discovered, but at that particular time, it was 85 degrees. An hour later, second measurement was 80. So 85, and in an hour, it went down 5 degrees. Assume the time of death corresponds to a t is equal to 0 time, and that the core temperature at the time of death was 98.6. So they want us to determine how many hours has elapsed before the bond. So typos. The body was found. And that time stamp that we're going to use is going to be T1, just because we don't know what it is. So let's let another random variable be that time, and then we'll figure that out, hopefully. All right, let's do this. Oops, I'm not really all that prepared here. Sorry, I was talking to the previous teacher. Kind of got me off guard a little bit. All right, we'll start off by setting some information that we do know. We do know that the surrounding temperature, that's T sub m, is going to be 70. And I think that's all we know. Or we also know that at time t is equal to 0 is 89. So let's write down some pieces of information that we can use. We can use that T sub m is going to be 70 degrees, and whatever the function is at 0, our starting temperature was 98.6. And then we'll use this differential equation to begin solving. D capital T dt is going to be equal to K. This is T minus T sub m, which is 70. So we might as well just put 70 there right now. By the way, since this is a cooling, there's no explicit negative sign in front of the k, so when we solve for this, we're probably going to find that k is going to be a negative number because it's going down. All right, now that we have that, this is a separable differential equation, which we can solve for. This is also, I mean, we're in a section called linear modeling, so we can also treat it like it was a linear function, so maybe we'll do that. As a linear function, we can write dt minus k capital T is equal to negative 70. And we have this idea of a, what's it called? An integrating factor. Mu is equal to e to the integral of the p, which in this case is negative k dt. Yeah, question?
Wouldn't it be negative 70k?
Yes, thank you.
Thank you.
Negative 70k. Okay, and so our integrating factor is e to the negative kt. And I think we've shown already that we can save the plus c and put it there later or whatever. And so we multiply by this for the whole thing. Then let's not go through all that big mess anymore. Let's just say ddt of e to the negative kt times capital T is the left-hand side. And then we'll have negative 70k, which is a constant, times e to the negative kt on this side. So this is the point where we integrate both sides. And then we will get e to the negative kt times capital T is equal to, now the integral of this will generate a u substitution. We just kind of do this off to the side. U is equal to negative kt. du is going to be negative k dt. So there's a negative k and a k here and a negative sign that would cancel. And so we just have 70 e to the u, and the antiderivative of that, which is going to be e to the negative kt. And we throw the plus c in here now because we have taken the integral. And then we divide out, we get t is equal to 70 plus, I'm going to divide, this is divided with a negative power, so it's like being multiplied with a positive power, c e to the negative kt. Oops, positive kt. I just said positive power. So that's your differential equation, or that's your general solution. But we have an initial condition that we can use. And so we'll use that initial condition to say that when t is equal to 0, when little t is equal to 0, big T is equal to 98.6. And then that will give us C is equal to 28.6. Because e to the 0 is 1, C is just going to equal 98.6 minus 70. And then that will give us our real, well, whoa, sorry, don't know what happened. Our actual particular solution. Now, our particular solution is, there's an issue with our particular solution because we have a k that we still don't know. So we need to solve for K. Unfortunately, we still don't know what this K is. So what we're going to need to do is we're going to need to use a couple of pieces of information that they have here about when they found the body, the temperature, and then an hour later after they found the body, and what the temperature was. All right. So per their suggestion, we will use T1. The temperature was 85 degrees. And then an hour after that, T1 plus 1, then the temperature was 80 degrees. So there's a temperature drop. So what we want to do is we want to take those two T values, the T1 and the T1 plus 1, and put that into the original, well, not the original, but the particular solution that we found. So in our first equation, we would have the T of T, which is 85, the T value, the temperature, is 85. 70 plus 28.6 e to the k times, this is where we put T1. And then for the second one, we have 80 is equal to 70 plus 28.6 e to the k times an hour later, which is T1 plus 1. So what we want to do is we have two equations, two unknowns, the k and t, and we need to solve for one of them. I don't know what we should solve for. Oh, we need to find t. We could find k to complete our analysis of what the function is going to be, or we can just solve for t1 and then call it quits. So either way, we can do it. But in terms of solving for t or k, I think we can rewrite the second one. Well, let's see. Let's write it so that we can get rid of, get e to the kt1 by itself. So I'll subtract 70, so I get that's 15. 15 divided by 28.6 is going to be equal to e to the k times t1. And then I'll do the same thing here, except I'm subtracting it from 80. So 80 minus 70 is 10. And then I'm going to rewrite this also because it looks like it's e to the kt1. Let's write that clearer. Times e to the just plain old k. So I think if I solve for e to the kt1, I can find e to the k, and then eventually find k. So I think my idea is to get use a substitution between these two. I'll put this value in for e to the k t1, and I will get 10 divided by 28.6 is equal to 15 divided by 28.6 times e to the k. So I can subtract or divide out, multiply by the reciprocal or whatever you want to do. I think I'm going to get 10 over 15 or 2/3. Two-thirds is equal to e to the k, so it looks like k is going to be ln of 2/3. Okay, not necessarily what I wanted to find, but we'll work with that. And the t1 that we're actually looking for is in either of these, but let's go ahead and pick on this equation over here and put this information to get our value. So 15 over 28.6 is equal to e to the ln of 2/3, that's k, times t1, and I want to solve for t1. Before I take the ln of both sides, I can kind of see that, well, how can I solve for this? I think I do need to take the ln out. So I'll need to take the ln of both sides. Is equal to the ln of 2/3 times t1. And so t1 is going to be the ln of 15 over 28.6 divided by ln of 2/3. Hope that's positive. I know that ln of 2/3 is negative because the 2/3 is less than 1. And so that makes sense because we expected our k to be negative. So 15 over 28 is also less than 1, so that's good. So this is negative, and this is negative. So given that those two things are negative, negative divided by negative is positive. I get t1 as a positive number. If anybody wants to punch that in the calculator and share the answer, that would be great. I will, meanwhile, rewrite our actual function. Not that they're asking for this, but the temperature is going to be given by 70 plus 28.6 e to the, and then here's the ln of 2/3 times t. And then the time, 1.591, thank you, Dylan. So T1 is equal to approximately 1.591. And this is going in hours because they're talking about an hour later. So the body was found about an hour and a half, a little bit more than an hour and a half ago, so then you can register the time of death and continue on with your investigation. So if you're working for CIS, you probably don't want to go through all this differential equations, and I'm sure they'll have formulas to estimate the time of death. You know, take the temperature at one point in time, and then they could take the temperature again at another point in time, put all the stuff in the computer, and then it'll spit out the answer for you without us having to go through all this mess. But this is how we can see according to Newton's law of cooling, this is how we can determine the time of death. Okay, questions? Alrighty. Let's go to our next topic. Oh, circuits. So the next one has a lot of information. Again, hopefully it's some stuff that you've already seen in section 1.3, and we're setting up circuits. So we have letters and all these terms that you may or may not be aware of. A loop can contain inductor, resistor, and capacitor. And then you're looking at the current in the circuit after a switch is closed, denoted by I. So I is the current. The charge on the capacitor at time t is going to be denoted by Q. So those are our two functions, I and Q, whatever might be relevant in the problem that we're doing. The letter L, R, and C are constants, or sometimes they're constants, sometimes they're functions, it seems like. They're known as inductance, resistance, and capacitance. So L is inductance, R is the resistance, and C is capacitance. And generally constants, but not always, as we're going to see in the problem that we're going to do. And then there's Kirchhoff's law that says that the voltage on a closed loop must be equal to the sum of the voltage drops in the loop drops contributed by an inductor resistance, a resistor and capacitor. And by the way, there's also a relationship between the current and the charge, and that's the derivative of the current is equal to, or the derivative of the charge is equal to the current. So here's an example of a complete loop that has an inductor, resistor, and capacitor. L usually measures the inductance, and it's given in henries, I guess. H, R is the resistor, given in ohms, and C is the capacitance, given in farads. And if we're going to add them all up, we're going to have L times di dt, that's the inductor, plus R times I, and then plus 1 over C times Q. So that's the voltage drop that you're looking at. And so since I is the derivative of the charge Q, you can write di dt as the second derivative of Q. Instead of just the first derivative of I, you can write it as the second derivative of Q, since they have that relationship. And looking at the voltage drop across the resistor, it's R times I, but again, I is equal to the derivative of Q, so we can write dq dt. And then the capacitor contributes with 1 over C times Q. So now, as a function of Q, we get a second order differential equation. Now, we can't solve a second order differential equation yet. So we hope that none of our problems are going to be second order differential equations. And it turns out that if you eliminate one of these things, then you're just contributing two things. And so we'll look at two possibilities that we're gonna see. The first one is called an LR circuit. And an LR circuit only has information about the inductor and resistor. And it's going to be given by L times di plus I times R. And then that's equal to the voltage. So if you have an LR circuit, you have a first order differential equation that looks like this. You can also have an RC circuit. And in an RC circuit, you only have the resistor and capacitor involved. And those two, the R is matched up with a current, which is I, but I again is equal to the derivative of Q. And so we have R times dq dt plus 1 over C times Q. So in an RC circuit, you'd be looking for the charge. Okay. All right. So here's our example. For our example, we're going to look at an LR circuit. An LR circuit has a variable inductor. So your inductor is not constant. Ooh, usually they're all constants, but now your inductor is not constant. It's not only not constant, it's not only variable, but it's variable and then it changes. So it's a piecewise function. So LR circuit has a variable inductor with an inductance defined by L of t, which is going to be in two pieces. So it's 1 over 1/10 t, as long as you're between 0 and 10. And then after that, it has no more inductance, and so it's going to be 0 for the rest of the way. They want us to find the current I, which is a good thing because this is the differential equation that we need to use. It has an I in it. We want to find the current I if the resistance is given by 0.2 ohms and the voltage is constant at 4. And then we have an initial value of 0 at time 0. Okay, so this is our guy right here. Guess I should just write it down. L times di dt plus r times I is equal to E t. All right. So now that we know that, we can set up our differential equation. And oh, by the way, it's a piecewise function, so we're going to have to do this in a couple of pieces. We'll start with the first piece, going from 0 to 10, since this is our initial condition. Our initial condition involves 0. So we'll start off with the L function being 1 minus 1/10 t. So between 0 and 10, we'll say that your differential equation then will become 1 minus 1/10 t times di dt is equal to your resistance. That's not equal to, sorry, it's a plus 0.2 ohms times the current again is equal to your voltage, which is constant at 4. All right, here's our differential equation. If you're looking at the I as your dependent variable, this is a linear differential equation. And we usually like to see our linear differential equation where in normal form or in standard form without this thing here. And I think if we rewrite this expression 1 minus 1/10 t as t minus 1 divided by 10, it might be easier to, mess around with, divide, and do all kinds of other stuff. I hope I did that right? Is that right? No?
I think t
Minus 10?
plus 10, right? It should be minus t plus.
Yeah. 10 minus t. Yes, thank you. All right. So now we can, if we're dividing it out, we can think about multiplying by the reciprocal, so we can try to keep track of where these things go. Anyways, the whole point was to be able to rewrite it as di dt plus, now let's divide everything by this, which is multiplying by the reciprocal. I have 10 times 0.2, I think that's just 2, divided by 10 minus t times I, and then I have 10 times 4, which is going to be 40, divided by 10 minus t. So now it's written in a nice form that we can deal with. It's a first order linear, and we can do that process of finding the integrating factor. So, oh, this is not, is it easy? Yeah, it's not too bad. This is the integral of 2 divided by 10 minus t dt. Let's focus on that a little bit. I think a u substitution, right?
Yep.
Would give us an ln, but the u substitution will come out with a negative sign, and then there's a -2, so e to the -2 ln of 10 minus t. And we won't worry about the plus c because we know what happens to the plus c. And if I want to simplify this, I think I can put this as a power, the -2 as a power of 10 minus t, and then the e to the ln of something will be something. I'll just be 10 minus t to the -2 power.
Oh, I have a question.
Yeah.
Oh, just about the integral. Why is it ln again? I know the integral of 1 over x is ln, but Because does the 10 minus affect anything?
Not really. I mean, technically what we did here is a u, du, negative dt. So it'll be the integral of negative 1 over u du. Oh, and then there's 2, put the 2 out there. So this is generally what we did.
Okay, yeah, that makes sense. Okay.
Okay, so now that's our integrating factor. When I say that, I mean this is our integrating factor. And so skipping over some steps, we know that the left-hand side would be a perfect product rule, and the product will be this term times I, and this is equal to this thing times this, so 40 10 minus t times 10 minus t to the negative 2 power. I suppose we can rewrite that. I should rewrite that because we're about getting ready to integrate this. This is 40 times 10 minus t to the negative 3rd power. Right?
Yep.
All right. Now let us integrate. I mean, all sides, but we really just care about what's happening in the last slot. In the first slot, we know that's just going to be the 10 minus t to the negative 2 power times I. And then here, we have a 40 constant, and then the u substitution again will generate a, wait. Okay, cool. The u substitution will generate a negative sign. And this would be, you add 1, so plus negative 3 plus 1 is negative 2, and we'll divide by negative 2. So there's a negative here, and the negative 2 will give me a positive. 40 divided by 2 will give me a 20. And I'll have 10 minus t to the negative 2 power plus c. Okay. So I want to solve for I. And these two are exactly the same. So when I divide, that would cancel out, and I'll just have a constant 20. And then this would be c times, well, it's divided by this, but it's like multiplying with a positive power. So let's just multiply by 10 minus t squared. Looks like that's it. Well, except we should probably put in our initial conditions. So we're good here with a general solution. Now let's put in our initial condition, which is I of 0 is equal to 0, I think. So in here, we're going to get 0 is equal to 20 plus c times 10 minus 0 squared. That's 100. Positive, subtract 20. 20 divided by 100 is 0.2. Negative. Okay. So that's your C, and then now you have your particular solution. I of t is going to be 20 minus 0.2, 10 minus t squared. All right. We'll box this. This is your particular solution. And now that you have your particular solution, what are they asking? Oh, this is good for I goes from 1 to 10. And so what we want to do is we want to hook this up with I, when t is bigger than or equal to 10. So we want to know what happens when I is equal to 10, or when t is equal to 10, sorry. 20 minus 0.2, this is going to be 10. 10 minus 10, and that's going to be 0. This is 0, so this is 20. So it looks like your I at 10 has to be equal to 20. Well, let's actually hope that that'll fit in our equation. So let's set up what our equation should look like from 10, t bigger than 10, based on our equation. So it's going to be L, what's L equal to? This is your L, and it's 0. When t is bigger than or equal to 10, it's going to be 0. So according to our formula, 0 times di dt plus 0.2 times I is equal to 4. Well, this is gone, and I just have this, which gives me a formula for I. 0.2 I is equal to 4. Let's divide by that. I is equal to 20. Good, because that matches with what we have. All right, so I think we have our answer. So our answer will be a piecewise function. Your current will be given by 20 plus 0.2 10 minus t squared, as long as you're going between 0 and 10, and then constant 20 when you're bigger than that. Okay? And I think they want us to graph. If we were to graph this, I know a couple of key points that we need on the graph for sure. We have an initial condition of 0, 0, and then we just found that when t is equal to 10, I is equal to 20. So I'm going to put that here. After 10, it'll just be constant, so that's just going to be a horizontal line. Between 0 and 10, it's this. This looks like it's a parabola. It's an upside down parabola. And if I were to find the vertex, this is already in vertex form. So the vertex, I think, is x is equal to 10, or t, and 20. So that's right here. That's perfect. This is a vertex. So it'll just be a parabola. The rest of the parabola, not that we need to draw it, would look something like this. But we only need the piece between 0 and 10, so I think that's good. All right, questions?
No, but on the piecewise function,
Yeah.
t is less than 10, and then t is greater than or equal to 10. Yeah. Oh.
No, I took the wrong one. I was trying to be slick. All right, I'm spending way too much time on this. I just delete it and then just redraw it. There. Cool. Good eye, Don.
Oh, I have a question.
Yeah.
So when we did the first part of the piecewise function, why did we try to solve what t is when t is equal to 10?
Because we have to remember, we want our function to be continuous when we have a piecewise function. And so we want to know what happens after that. And so right at 10, although this says it's not equal to 10, but we know that it's approaching 10. And when it's approaching 10, we want to know what happens to it. And so it's like taking limits. When you take limits, you end up just putting the value into the expression to get the limit. So that's kind of like what we're doing.
Okay.
Okay, anything else? Okay. Next one, drug dissemination. Can we skip this for now, and hopefully we'll come back. I think we do have some time, but I want to get to 3.2, the nonlinear models first. And so let's do the 2 examples I have for nonlinear models, and if we have time, we'll come back and do the drugs. I mean, you know, that problem. All right, so a nonlinear model, this equation here apparently is not linear. Can somebody tell me why it's not linear?
Because p is to the second power.
If you distribute that, you'll have p to the second power, so it's no longer linear. Good. So this is an example of something that's not linear, but it is also, if you work it out, it's almost linear, except you'll have a p squared, which means you can probably use Bernoulli's to solve for it, or there's no t's around. So there's no t around, then it probably is separable. You can get all the p's on one side. Not only separable, but what do we call a differential equation where we only see the dependent variable on one side?
Is it autonomous?
Autonomous. This is an autonomous differential equation, which we solve by separating the variables. So this is separable. All right, let's do this example using this logistic model. It says a number n of supermarkets throughout the country are using computerized checkout system described by an initial value problem here. dn dt is equal to n times 1 minus, and then you have 1, 2, 3 zeros and a 5 times n. And they have an initial condition of n of 0 is equal to 1. Because this is an autonomous differential equation, we can use phase portrait concept to kind of predict the expected number of supermarkets that would eventually adopt this computerized checkout model. So how's this going to look like? We will, phase portraits. So remember, a phase portrait is a one-dimensional phase portrait, to be more specific, is going to be a phase portrait that's really just an axis, and we choose the vertical axis because it's usually would be representing the dependent variable. And then we find the zeros of that. So n is equal to 0 is a 0 of that, because we're really looking at n times 1 minus 0.123, zeros and a 5. And we're setting this equal to 0. So we have n is equal to 0 is one of them. And then if we solve for this, and we're going to get n is equal to n is equal to 1/5. 1/5 is like 20%. And zeros, is it 200, 2,000, 20,000? 1 divided by 1, 2, 3 zeros, 2,000. And then our face portrait should tell us what's happening between. So if we For example, pick a number that's less than 0, which we probably wouldn't do since you're not going to look at the negative number of supermarkets. But if we did pick a number that's less than 0, this would be a negative, and this would also be, well, negative is positive, so this would be a positive. So this would be going down. It'll give a negative contribution. But we're not doing anything below that. Let's find a number between 0 and 2000. So the first n would be positive, and this would be 1 minus a number that's probably going to be less than 1. So this will remain positive. So it looks like this is going to be positive going up. And then if we put a number that's bigger than 2000, like 1,000,000, I'll have a positive for this first one, and I have 1 minus something that's really big that would make this into a negative. Negative times a positive is a negative. So our phase portrait would look something like this in terms of some of the words, vocabulary that we were using when we were studying autonomous differential equations. We can say that n is equal to 0 is a what kind of equilibrium point? You remember those words?
Is it like attractive or something?
Attractor. So 0 would be what? I don't think it's attracting. That's what? Repeller. It's repelling. So it's 0 is a repeller. 2000 is an attractor. I think they also called it, well, I was going to say sync, but I think they do that for two-dimensional phase portraits. Oh, what's the other word? Stable. Unstable, stable, and semi-stable. So we can conclude that we have a stable equilibrium at 2000 and an unstable equilibrium at 0. But again, we don't care about what's happening below 0. In fact, when n is equal to 0, or when t is equal to 0, n is equal to 1, so we know that we're bigger than 0. And based on this, we know that 0 is an asymptote, and we know that 2000 is an asymptote. We know that we're going to be strictly increasing, and we also know that we're going to have some sort of exponential growth or logistic growth. And so we can imagine the graph should look something like this. Without solving for anything yet, we can already picture what the graph would look like. And so based on this graph, it looks like in the long run, in a long period of time, we can say that they're going to be approaching 2000 as our ceiling. So we could say limit as t approaches infinity of the function, whatever function it is we're solving for, is going to be 2000. All right. Now they want us to actually solve for this differential equation. So let's take that differential equation and solve for it. And we will use our separable differential equations technique. dn dt is equal to n divided by 1 minus 0.35n. So we separate it, we get dn divided by this, the whole thing, because those are all your variables. Now what? How do you solve for this differential, or how do you solve for this integral? We're going to integrate both sides here. Well, the right-hand side is going to be t plus c. Any ideas what this left-hand side is going to be? I'm going to go ahead and start Wolfram alphaing it. By the way, are you guys doing this? Are you guys using an integrator, an integrating program?
Yes.
What?
Yes.
Yes? Anybody on Zoom using an integrating program? Because if you can share your results. I'm gonna, whether you use Wolfram or Symbolab, after you've ran whatever it is that you're solving for, when you use X or whatever, 1 minus 0.0005 times X, and we'll just say dx. So maybe as you guys are participating, and I ask for help in solving, you can run in whatever program you're using. Again, whether you use Wolfram Alpha or Symbolab or something, you can always get the result by copying the URL. Anyways, this is what it looks like we got here. So I'd be interested in combining this into, because I'm eventually going to want to solve for capital N. So I'm going to be interested in combining this into one expression or one term. And the natural logs have these special properties of finding ways to combine and to take them apart. So I think this will be the ln of x divided by 0.0005 x minus 1, because they're subtracting. So I'll take that piece of information and use that for the antiderivative. So this will be the ln of n divided by 0.0005 n minus 1 is equal to t plus c. And we'll take the e of both sides. N divided by 0.0005 n minus 1 is equal to e to the t plus c. Oh, the plus c there is in the power, so you can think about it as e to the t times e to the c, which we can just call a. We can solve for, we have an initial condition, n of 0 is equal to 1. So we can solve for that here, solve for the constant a now, or we can solve for it later. Let's solve for it here. N of 0 equals 1, so this would be 1 divided by 0.0005 times 1 minus 1. Maybe we should have solved for it later. Oh well. A e to the 0, so that's just a is equal to 1 divided by, what is this? One divided by, I need parentheses, oh, I need a graphing calculator. Let's try that again. 1 divided by parentheses 0.1235 minus 1, oops, minus 1, close parentheses. Delete. There we go. I got negative 1.0005 and more stuff. Negative 1.0005, 0025. Maybe I'll stop here. We still need to solve for n. I'm going to hold off on this for a minute, because it seems like carrying that big decimal around might be more work than it's worth as I'm trying to solve for n. So let's multiply both sides by the denominator. 0.0005 n minus 1, distribute 0.0005 n a e to the t minus a e to the t. And then I'll bring that over to the other side. And then I'll factor out an n. Now it's by itself, and I'll divide by this stuff. So this is a e to the t divided by 1 minus 0.0005 a e to the t. And then this is where you put in the a value. So this will be a positive, because there's a negative in front here. So let me write n of t is equal to 1.0005 e to the t divided by 1. Okay, I have my last number here. I'm going to multiply this by negative 0.0005. And I just got 0.0005 again. Is that right? Yes, so. Wow. I think that's what I got. So this is our particular solution to our differential equation. Okay. Questions?
Oh, I have a question about the stuff we did earlier, like when we drew the graph.
The circuits?
Oh, no, it's still about this problem. It's just like the earlier part of this problem.
Yeah.
Yeah, so how do we know that the graph is going to have that shape again?
Because we have asymptotes at 0 and 2000. And we also know that if you're going to be your starting point here, is when t is equal to 0, n is equal to 1. That's your starting point. And we know that we have an asymptote at 2000, so this is going to go, it's going to come from an asymptote, and then it's going to go up, and then it's going to end in an asymptote. We know it's not going to go beyond 2000, or we know it's not going to go below 0, because those are the rules for autonomous differential equations, is that your functions have to be between two equilibrium points. And your functions are either strictly increasing or strictly decreasing. And they have to hit the asymptote. So all the graphs are going to be shaped like this, regardless of what your starting point is. If your starting point was up here, then your graph will be, you know, more like this probably.
Okay, so whenever you have like two asymptotes, usually the graph looks like that.
For autonomous differential equations.
Yeah. Thank you.
Okay. Any other questions? All right. We have one more to do. Oh, I think this was this crazy problem that we had in the homework. I think I'm gonna need to look at my notes for this. Because I vaguely remember how we got this problem figured out from section 1.3. But the idea is to find the problem. So determine the differential equation from a mass sinking in the water that imparts a resistance proportional to the square of the instantaneous velocity and also exerts an upward buoyant force, which is whose magnitude is given by Archimedes' principle. Assume that positive direction is down. Let V, capital V, be the volume of the object. Rho is the weight density of water, and the gravity, G, is the acceleration due to gravity. All right. So, according to how we solved, or how we came up with the differential equation last time, let's see if we can go through the steps here. We have force is equal to mass times acceleration, and our acceleration is due to gravity, so mg. Notice that the g is going down is positive, so we're not going to throw a negative sign in front of that. And Archimedes' principle, buoyancy or upward force, is equal to the weight of the water displaced. So let's figure out the weight of the water displaced. Archimedes. Weight of water displaced. Is going to be, I'll call it F sub A for Archimedes, the density times the volume. So we have density times volume. Resistance imparts a resistance proportional to the square of the instantaneous velocity. So we need the V, capital V for the volume, but we also need a little v for instantaneous velocity. So let's make sure you write your little v and capital B a little bit differently. So the resistance proportional to the square of instantaneous velocity. So resistance is also a force, let's call it F sub R, is proportional to, it's K times the square of the velocity. So little v squared. So little v and big V are different. And so the total force will be these forces added together. Total force will be mg. Let's call this capital F. Mg is equal to, or mg weight displayed or displaced by the water, and then the resistance. So the positive is going down, so the resistance is pushing it back up. So that's a negative resistance. So we'll call that minus F sub R. And then the weight is also, we think of the weight as being pulled down, but since going down is positive, we're gonna put a negative in front of that. FA. So this is your force, and this is equal to mg minus kv squared minus rho capital V. And so this is a force, and Newton's law says force is equal to mass times acceleration, and acceleration now is the derivative of the velocity. So let's call this, well, let's solve for A first, and that's just dividing out the m. So mg minus k v squared minus rho capital V. And then acceleration is going to be just the gravity, because the masses will cancel, and all these other terms will have a mass in the denominator. And then now let's change this to a dv dt, because the acceleration is the derivative of the velocity. So this is your differential equation. And I think this is the answer that we had in our problem in section 1.3. So now that we have a differential equation, they want us to actually solve for it. And if you look at this, g is constant, rho is constant, the volume is constant, since we're talking about a fixed volume, the mass is constant, your constant of proportionality is constant. So really you just have v by itself. So this is a separable differential equation. Actually, let's write this as dv dt is equal to g minus and kv squared minus rho capital V divided by m. So we can then rewrite it as dv little v divided by, well, I was going to divide by, but let's write it as m, the denominator, k little v squared minus rho capital V. So it's this, and if you look at this, this is your variable v squared. So you can do a variety of things. You can probably factor this, since this, you can look at this, force this to look like a difference of two squares, or you can find some other formula. If I can, let me just get to, well, I can get to the answer, but the answer looks really, really messy. Anyways, let me just write the answer down. V of t is equal to, okay, where did A come from? Oh, I have to come up with more variables. All right, this is gonna get too messy if I try to write it in less than 2 minutes. So maybe this would be one of those things that I can make a video for and post in our notes. All right, we're out of time. And I think that's it anyway. So we got section 3.1 and 3.2 done. Next time we'll talk a little bit about 3.3, and then we'll get ready for the test next week. Okay?
So we won't talk about the drugs.
No, we didn't have time. Sorry, no drugs today. I suppose I could do a video on that too. Okay, that's it. I will stop recording.
Thank you, Professor.
Thanks, Bill. Thank you. Shana, hey. All right, stop recording.